Hey guys, in this lecture we are going to talk about earthquakes. Specifically, we are going to be talking about the types of waves that are seismic waves that earthquakes release. And then we will be talking about the types of faults where the plates meet. And then we will finish up with how earthquakes are measured. All right, so in the last unit, we talked about plate tectonics. And so hopefully by looking at this map, you can see that there is a definite relationship between earthquake activity and plate boundaries. So you can kind of see in this image of the globe that they're closely related to where plates are going to meet. So at the boundaries between those plates, the friction is going to cause them to stick together. And when that energy is built up, it needs to be released. And when it is released, that's when we see earthquakes. So why and where do earthquakes happen? So again, like I said, they're going to be caused by the vibration of earth produced by the rapid release of energy. And these are massive amounts of energy. The more destructive the earthquake, typically that means that more energy has been released. Earthquakes are going to occur at those plate boundaries that we talked about in the last unit, and we give them the name that is fault. And there's different types of faults, and we'll talk about each of those later. When that energy is released, it's released in the form of seismic waves. And then we're going to specifically talk about those seismic waves. We've talked about them a little bit in earlier units, so hopefully this is kind of a reminder and a review for you. All right, so let's introduce some terms. So we're going to see the terms focus and epicenter. So the focus is going to be the underground origin, okay? So you're going to see it on the underground. Now the epicenter is going to be the point on the surface, so it's directly above the focus. So the focus is the underground origin, and the epicenter is going to be directly above the focus on the Earth's surface. So again, you can see the focus is going to be the underground origin of the earthquake. The epicenter is going to be directly above the focus on the surface of the Earth. Again, here's just another image for you. So you have your focus and you have your epicenter. And in this image, you can see these represent the seismic waves that are being released by the plates coming together. So what are the different types of waves that are going to be released when an earthquake happens? So there's two types of body waves. The first one are going to be P waves or primary waves, and the second type are going to be S waves or secondary waves. So make sure you're paying attention to what's happening in each one. So you can see in a P wave, there's compression, okay? And in an S wave, it's going to be moving up and down. So in a P wave, we have compression, and an S wave, we're going to have up and down motion. So here's another image, just going to use an example of a slinky. So it's compression. We're going to have those compression of matter, and in this case, it would be the earth, and then decompression or expansion. And this we have the particle motion is going to be an up and down, almost like a wave. Another type, or let's just specifically talk about P waves. So P waves or primary waves are going to arrive first. Remember, primary means the primary pressure waves. And they can travel through solids, liquids, or gases. Again, we see the compression of the P wave. S waves or secondary waves are going to arrive second. An S wave is slower than a P wave, and it can only move through solid rock. It's not going to move through any liquid medium. So as we move along in the unit, it's good to remember P waves and S waves. Remember, P waves are going to arrive first, and S waves are going to arrive second. This is important when you're reading a seismograph, so make sure that you are remembering P waves arrive first, and then those S waves arrive second. Now we're going to talk about surface waves. So the P and the S waves are body waves, and now we're going to talk about surface waves. And so these are the slowest of the three earthquake wave movements, but they're typically the most destructive. So the first type are going to be love waves, and then the second are Rayleigh waves. So love waves are going to move up and down and side to side, okay? So this is where the most damage comes to structures, comes from these love waves. So you're going to move up and down and also side to side. So you can kind of really see that movement at the end right here in this animation. So you're going to be moving up and down and then also side to side. Now the Rayleigh waves are going to be orbitals. They're going to be moving in a circular pattern. And so almost like that wave, water wave motion again. So here's another image for you guys too. So we're moving up and down, then we're also moving side to side. And in the Rayleigh waves, we have that circular motion. We've already covered this a little bit, but scientists have used seismic waves to study the Earth's interior, and because of these waves, they can or have determined the different matters in which the Earth's layers are in. So both the S waves and the P waves travel throughout the body of the Earth, and they're going to be picked up by seismometers, and you guys are going to learn how to read seismographs later on in the unit. So remember, we've used these seismic waves as ways to determine the inside of the Earth. So we know that P waves are only going to travel through solid and liquid. So they're actually going to move throughout the Earth. So if this represents the Earth, we have our earthquake focus. The P waves, or the primary waves, are going to be the first ones, and they're going to move through that solid. And then they're also going to move liquid and then also solid as well. Now we know that S waves can only travel through, or cannot travel through liquids. They can only travel through solids. And so from this, we know that that outer core is going to be a liquid. Now scientists believe that the inner core is a solid, but we don't know exactly because we haven't been able to have any waves that can travel through that liquid and through the solid. Because remember, the P waves travel through both liquid and solid, but S waves can only travel through solids and not liquid. So there's really no way of definitely knowing if that core is a solid, but they're pretty sure of it. All right, so now we're going to move into fault types. So a few different terms that you guys should be aware of as we're moving through. So we have a footwall. Okay, the footwall is going to be the plate that doesn't move. The hanging wall is going to be the plate that does move. And the fault plane is the plane along which the break between the two plates occurs. And then the last one's going to be the fault line. And this is the line in the surface of the Earth caused by the fault plane. And you can actually see these on the surface of the Earth. So let's just take a little bit of a review. So in the last unit, we talked about different types of plate boundaries. So we have divergent boundaries. Okay, this is when the plates are moving apart. Convergent is when they are bumping up against each other. And then we have transform, which is when they're sliding past each other. So now let's talk about different types of faults. So the first one's going to be that strike slip quake or fault, and it's going to happen at the transform boundaries. So this is when the two plates are sliding past each other. This is going to be a normal fault, and this is where the hanging wall is going to move down. Okay, so the hanging wall is going to move down. Then we have our reverse thrust quake. Oops. And that's when the hanging wall is going to move up, okay? And this happens at convergent boundaries. So normal means that our hanging wall moves down, okay? That's at a divergent boundary. A reverse is when the hanging wall is going to move up. So remember, our hanging wall is the plate that moves, okay? Your foot wall does not move. And then the last two types of quakes that we have are horst and graben quakes. So horst represents a block that's going to be pushed upward, and the graben's going to be the exact opposite, and it's going to be a block of the Earth's crust that moves down. So here's just some more images. So this is going to be that strike slip earthquake, okay? And so they are moving past each other. You'll also hear the strike slip fault, okay? So the two plates are literally sliding past each other. So here's some images of that strike slip fault. So you can see they're sliding past each other. So you're not going to see any plate that's going to be above or below the other. So you can see it moving. Okay, so the land is relatively even, but you can see that the actual plates have moved. You can see that by the direction of the road it's being split. Again, the fence at one point was connected and now they're separated, and that's because of that strike slip. They're moving past each other. Now we have our normal earthquake, so your foot wall and your hanging wall. So again, you can see that drops down. Again, dropping down. So these are pretty crazy pictures. Last is going to be our reverse, and that's when our hanging wall is thrust up. So you can see here, moving up. You can see the movement of this plate is up or thrusted up. And this is another one where it's thrusted up, so you can see a lot of damage that's been happening from this particular type of earthquake. Then we have the graben, again, when that's going to be when the plates kind of move apart and it falls inward. I know I'm moving kind of fast. I'll post these notes so you guys can look at the pictures. Then we have the horst, and that's when the piece of the earth is actually thrust up. This is a pretty good picture because you can actually see it have been moved up. All right, so there's a lot of information on this page, and we're just going to go through it briefly. So how do we measure earthquakes? So there's three types that we're going to talk about, but there have been many ways that scientists have measured the earthquake strengths in the past. So the three that we're going to talk about today are going to be the Richter scale, the Mercalli scale, and the moment magnitude. So the one that you guys are probably the most familiar with or have heard of the most is the Richter scale. So the Richter scale is going to measure the amount of energy that an earthquake releases. So each number is going to be 10 times stronger than the number below it. So a lot of times you'll hear, it was 4.5 on the Richter scale. So if something is 5.5 on the Richter scale, then it's 10 times stronger than an earthquake that's 4.5. Then we have the Mercalli scale. It's going to measure the amount of damage. So rather than measuring the amount of energy, it's going to measure the amount of damage. And it's going to be in Roman numerals 1 to 7. And it's going to be based on common occurrences. So by observing at what type of damage it's caused. And then the last one is going to be the moment magnitude. So this is going to be the scale that geologists use today, and it's going to be looking at the total energy released as well. And can be used for any kind of earthquake, near or far. So some of these have problems with measuring earthquakes that are far away. So like the Richter scale is really good at measuring things that are earthquakes that are close, but not necessarily earthquakes that are far away. The moment magnitude is going to be good at measuring earthquakes that are close and then also far away. So some news reports may mention the Richter scale, but almost always it's going to be the magnitude number is from the moment magnitude. So here's the Richter scale. So you can see 2, 4, 6, and 8. So seismometers are only going to detect, something on the 2. You're not going to be able to feel it. If it's a 4 on the Richter scale, it's going to be felt by walkers, windows, doors rattle. 6, structural damage to houses. And something that's an 8 is going to be a total destruction. So your ground, you could actually see it rising and falling. Then we have our Mercalli scale. Remember, this is going to be measurement of damage. So severe damage, wide cracks appear in ground, waves seen on the ground surface. So you can kind of go and look through those. And the last one's going to be the moment magnitude. And this is kind of a cool image to look at because it's going to compare the energy equivalent. So you can see the magnitude 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then you're going to see the amount of energy equivalent. So a large lightning bolt is going to be about, I don't know, 3.2. Average tornado releases just under 5. An atomic bomb is just over 6. And over here are earthquakes that have happened in the past and where they've measured on the magnitude, on the moment magnitude. And you can kind of compare those to each other and get an idea of how much energy is actually released during earthquakes. All right, and that is it. And like I said, you guys, I'm going to post